Nano indentation
is an alternative technique to measure the mechanical properties of various materials. We can apply this technique from all range of materials, from polymers to composites. This is the experimental setup of instrumented nano indentation test. These are the various mechanical properties which can be measured using nano indentation, which are hardness, Young's modulus, stress-strain analysis, time-dependent creep measurement, fracture toughness, elastic and plastic work or energy of the deformed material, modulus mapping of the specimen, that is, how the elastic modulus changes from one place to another in the sample. Also, nano scratching of thin films and coatings can be done. Working of the nano indentation. Berkovich indenter is forced into the specimen at selected location in a continuous or stepwise mode. The load and displacement of the indenter are recorded during loading and unloading. Characteristic load versus displacement curves are then plotted. Schematic of the experiment is presented in this slide. At first, the indenter is pressed against the material. After attaining the maximum load, the indenter is held at this load for 2 to 3 seconds so that the material can recover its properties. The indenter is then reverted back, and this unloading is purely the elastic recovery phase. After this, a small impression is seen on the material surface, which is later on using AFM or techniques like some software's profilometers. Characteristic load versus displacement curve is shown here. Load used in this technique is in the range of 1 micronewton to several newtons. Depth varies between several tens of nanometer and several micrometer. During loading phase, load increases with time. After attaining the maximum load, holding is done, further unloading is done, and we can measure the elastic modulus, reduced modulus, by drawing a tangent from the initial portion of the unloading curve. Results of the experiment are as follows. Ultra-high molecular weight polyethylene based composites are used. Ultra-high molecular weight polyethylene has been chosen as the reference material. This is the load versus displacement curve obtained for ultra-high molecular weight polyethylene. The maximum attained load is 16 micronewton and the maximum displacement attained is 75 nanometer. This is the curve for ultra-high molecular weight polyethylene plus 2 weight % alumina. Here it is seen that the maximum load is still around 16 micronewton, but the maximum displacement is around 70 nanometers. This is the curve for ultra-high molecular weight polyethylene plus 5 weight % alumina composite. In this slide, a comparison between all three specimens has been presented. It is seen that minimum residual is least in the case of ultra-high molecular weight polyethylene plus 5 weight % alumina, while greatest in the case of ultra-high molecular weight polyethylene plus 2 weight % alumina. On the basis of this nano indentation curve, a conclusion can be made that 5 weight % alumina increases the hardness of the material up to 79 MPa and minimum indentation depth is also around 64 nanometer. These results show that ultra-high molecular weight polyethylene plus 5 weight % alumina composites show better mechanical properties than ultra-high molecular weight polyethylene, and also that ultra-high molecular weight polyethylene plus 2 weight % alumina are inferior to those of ultra-high molecular weight polyethylene alone. Also, addition of larger amount of alumina increases the mechanical properties while smaller amount does not. Thank you.